All right. Hello, everyone. I am back with another video, and today we're going to be discussing problem number 8 from the March 2020 comprehensive exam, which is all about using the divergence theorem to compute surface integrals and flux integrals. So let's take a look at the question. It says, let f of x, y, and z be the vector valued function z squared x, 1/3 y cubed plus tan z, x squared z plus y squared, and let S be the upper half of the unit sphere x squared plus y squared plus c squared equals 1 with upward pointing unit normal. Compute this right here is a flux integral, the integral of f dotted with ds. So normally to compute a flux integral, you can pretty easily turn it into a double integral by finding the parameterized surface, which is usually referred to as R of u and v, where u and v are our parameters, right? And then all you would have to do to turn it into a double integral is plug in R of u and v into f, right? So f of R of u and v, that'll turn it into an equation of 2, right? And then to handle the ds part, all you would need to do is find the normal vector, but the normal vector here is going to be dotted with the partial derivative of r with respect to u, crossed with the partial derivative of r with respect to v. And that's how we would find that. And for the unit sphere, we could pretty easily find a parameterization, but actually what we're going to do instead, so let me cross all of that out. We're not going to do that here. Instead, what we're going to do is we are going to use the divergence theorem. And the divergence theorem states that if we are trying to find the flux integral, right, of some vector field over some surface, what we can do is we can compute a triple integral that handles the volume, right, of that surface. So usually we would just represent that as v, and then what would we be integrating? We would be integrating the divergence of our vector field f. So it would look something like that. So this is actually what we're going to use today. And so in order to find that, we're going to have to find the divergence, right? The divergence of f. So what is the divergence? Well, the divergence is going to be our partial derivative gradient, right? Our partial derivative operator. And then that is going to be dotted with the vector field itself. So the divergence is going to be a scalar field because this will result in a scalar valued function. So that is going to be, let me expand that out here, partial over partial x, partial over partial y. Sorry, my pen's having some issues. Partial over partial y, and partial over partial z. So that is our gradient vector, right? And then we're going to dot that with whatever f is. And I don't want to write it out here, but you see up top that it is, again, z squared x, 1/3 y cubed plus tan z, and x squared z plus y squared. So taking a look at that, let's take the derivative, right, the partial derivative of our first component with respect to x. And when we do so, remember, we're treating that z squared like a constant. So that is going to give us z squared, right? Okay, that's easy enough. Then taking a look at our second component, maybe I'll zoom in. We're going to take the derivative of this guy with respect to y. So 1/3 y cubed is going to become y squared, right? And that tan z is going to basically disappear. So that's just going to give us plus y squared, right? Plus y squared. And then x squared z, right? Plus y squared. That y squared is going to go away, but we're going to be left with an x squared. So we're going to get z squared, right, plus y squared plus x squared, which we know is actually the equation for the unit sphere. So essentially, right, along this surface, this is always going to be equal to 1. So really, when we set up our triple integral, we are just calculating this. Where V is, of course, the upper half of the unit sphere. But we know, right, that when we have the triple integral of the unit function, or the unit function, which is just 1, right? That is going to give us the volume of that shape, right? So now we are looking at a 3-dimensional shape, and I can honestly probably draw it. I'm a terrible artist, but if that is our XY plane and Z is 1, it'll look like that. That's really bad, but you know what I'm saying. This is half of a ball. So how are we going to find that? Well, we actually know the volume formula for a sphere. So for a full sphere, SPH, right, ERE. For a full sphere, we know that the volume is given by 4/3 pi r cubed, where here r is just 1, right, because it's the unit sphere. So that's just going to give us 4 pi over 3. But this is a half sphere, right? We're only dealing with the positive z-axis. So really, we need to chop it in half. So that's going to give us, for V, the volume of V is going to give us 4 pi over 3 over 2, right? And that's just going to give us 2 pi over 3. So really, this whole thing is going to be equal to 2 pi over 3. So let me write that out. And then this is actually our final answer. So using the divergence theorem, we were actually able to simplify the math down a lot. And I actually tried to compute this using the normal method of computing the surface integral, where I found the parameterization, and then I took the partial derivatives and stuff, and you would end up with this giant integral that's all in terms of like sine phi and cosine theta, and you would get like sine to the 5th power of tan of cosine z. So it's really not even worth it to go ahead and do that. So whenever you know that you can use the divergence theorem, do that. And how do you know that you can use the divergence theorem? I believe that the requirements are you have a closed regular surface or smooth surface, and you don't have any singularities within your vector field, i.e. there are no points in your space over which the vector field is undefined. So if you had something like 1 over x plus y plus z, that would cause a singularity at the origin, right? Because 1 over 0 is undefined. But since we don't have this, right, with our vector field f, if you look at it, all of these values are going to be completely normal, and S, which is the surface that we care about, the upper half of the unit sphere, that behaves well. We really don't have any issues. So it's always easier to just, when you see this, use the divergence theorem, Stokes theorem, Green's theorem, really any theorem, depending on your situation, is probably a good thing to keep in the back of your head when you're doing vector calculus, because a lot of these problems are going to end up involving that. So yes, just an overview, right? We decided not to do it the traditional way. We used the divergence theorem, right? When we computed the divergence, we saw that it was just x squared plus y squared plus z squared, which on our surface is just going to be 1, right? And so then, right, we know that we're just integrating that over our 3-dimensional region, and that is going to be, right, that is going to be just the volume formula for the half sphere, which we can easily find without doing any calculus, right? We can just remember that the volume of a sphere is 4 pi over 3. So if you have any questions about that, please let me know. If you also have any requests or recommendations for problems that you want to see covered in the future, again, I would love to take a look at those problems. So hopefully you found this video helpful. Make sure to give it a like and a follow.